Today I wanted to walk through creating a point deform inside of Blender, or a surface deformer, but inside of geometry nodes so that we can have changing topology. They have a surface deform inside of Blender, but it doesn't work for changing topology, and I'll cover that later. So we're going to be creating this aspect of it. So we simulate on one set of geometry, and this calculates one time, and you can cache it out. And then if you want to basically move that over to another piece of geometry that's deforming, you can do that without having to create that deformation in the actual simulation itself. And so this is super useful for attaching from one set of geometry to another. To show in more description of what I mean, if I have this deforming animate grid and I move it in space, or even if I rotate it in space, you can see it snaps exactly to where it should be. So it's really useful for when you have a heavy calculation that you want done either on multiple frames or one frame, just one time, and then deforming it at the vertex level to another set of geometry. And it works with deforming geometry too, not just at the transform object level. So this is one example I have here, and then another example is this feet deform, where I have a calculation that I did on one single frame. So we have a convex foot, which I created around a rest foot, which is simply the foot animation here that I have here, which is just basically time shifted or frozen on the first frame. And then we want to have this convex foot, which I created like a makeshift boot around that foot. And I want it to be parented or follow the moving foot. And we don't want to have to recalculate that convex hull every single frame. So we just want to cache it out one time and then have it deform to the moving foot. This is the perfect example for this. So we've calculated our convex foot on one time. We have our rest foot. So this is referencing what topology is it where we're going from. And then we have our foot anim, which is what topology we're going to. And so this is perfect for that. So whenever I enable this guy, it snaps directly in the right place because we have a reference from where it should be and we're going to this foot. So this is what I mean. If you use a surface deform, you have to make sure that it's lined up perfectly, then capture it and then move it back. And then you can move in your timeline. But this is not procedural. We want to make sure it's procedural. In this particular case, we can move our deforming foot wherever, and it would snap directly into the right place because we've already cached the rest foot. So it's perfect for that. Okay, so here I built a small example of where I have 3 different shots. I have my original foot anim here. I have shot 20, which is here, and I have shot 30, which is here. I need to take, like, let's say you're working in shot 10 and you need to move the convex to the foot in shot 20. Well, the default Blender method, you can't, but with this rest position, with it being stored, you can very easily change it. So we can simply drag this shot 20 to attach it to foot in shot 20 over to here. So surface object, we just drag that in and boom, our convex foot is now seamlessly attached to the shot 20 foot. Oh, I actually need it in shot 30. We just drag this into shot 30 and now our convex foot is seamlessly attached to the shot 30 foot. It's as simple as that. This is why it's so useful, because all the information gets calculated here at the rest position and all the topology and everything is calculated there. And then all it's doing is finding the same topology but in a different space. And so that's why it's so useful.
And so I just wanted to point that out. The other problem with the surface deform is that it can't work with changing topology.
Okay, so to show that it doesn't work with changing topology, I'm going to add a surface deform modifier. I'm going to try to plug my deform animate into this object and hit bind. And you can see no vertices were bound. And we can try it on the deform grid too. And this also will just error out. I've tried on frame 1, I've tried on different frames, and it always breaks. So it doesn't seem to work on changing topology. That's why we need this method to just correctly snap it into the right place. I'm going to walk through downloading, installing, and just modifying a surface deformer that someone else created.
Now it needs to be said, I did not create this initial setup for this point deform inside of. This is due to another artist, very talented, who I will link. But yeah, his geometry network was super pivotal in helping me get this set up. So he deserves all the credit. I'm just here, saying, hey, download his tool. It's free. It's great. and it works wonderful. The only thing I'm changing to it is adding the option to have rest geometry. That's it. It's just this right here, which is just, you get your rest object. It's essentially like your time shift inside of Blender. And that's all I'm adding in his tool set. So let's get started. So this artist here, I'm going to link this website in the YouTube description. But Cardison Caramel, I might be pronouncing that wrong, but his Gumroad, he has a bunch of very useful tool sets for Blender. I think he actually helps create some of the geometry nodes I heard. And if you scroll down here to GN Surface Deform Modifier version 4, it's free, you can see, and you pretty much just download this guy. So this is the guy. I'm going to link it in the description. He has a bunch of other super cool stuff too. Make sure to check it out. Like, subscribe to his channel. He puts out a lot of really cool stuff. Shout out to him. And then you just want to say add to cart. So you say add to cart. You say 0. Or, if you want to support his channel, put $500 if you want. Support him. Support the artist. So add to cart. You hit get. And then you'll come to this page and it'll say download. You just hit download and here it is. And then you can just simply open up the file right from there. And here it is. This is everything. That's it. It's as simple as that. And then you can play by hitting spacebar on your keypad. And you can see how he did it. And what you can do is just, you can go to geometry nodes and you can literally control spacebar to go into his setup, and you can literally copy. Actually, what you can do, if you have a Blender file you want to apply this geometry nodes setup into, you can go up here to file and say append, and you'll just go find that file and you say append, and then it'll ask you what you want to append, which is really cool. And so we can actually go in here and say node tree, and then just say GN surface deform, and then hit append, and that'll take his geometry setup and put it into yours. And it'll also come with all the dependencies too. And I don't think in my case, I don't think I had to select each tangent, but that comes in with it, which is awesome. So I just hit import, and then I was able to just go over here to convex foot, go over here, add a modifier, geometry nodes, and then here you can actually, don't click new, click this one, and then type in, what is it, surface deform version 4, and there it is, and now you have it. And it's as simple as that. Now I made a modification to it, that's why this rest object is here and why this error is showing up, but for you that might not happen, and we're going to build that today. So that's kind of how that works.
So if you look inside of his file, the armature human, there's a body, and this is actually, this armature node modifier is applying the actual animation, but in the geometry nodes, so before this guy is applied, it's storing the rest position here. It's just grabbing the position and storing it as a point attribute as rest position. The name is rest position. This is storing on the body, and then after it applies the armature, that rest position is still stored on the body because it applies after. So it's basically storing what the position was at rest. But I figured it's kind of an inconvenience to have to apply that every time, to have to bake out the position on the first frame and then, do that kind of thing. So I figured it'd be easier to set up a rest object itself, which you can create by simply creating a rest geometry. So like in this other file, if I take, let's add another plane here. We're going to add a modifier, geometry nodes, and we're going to call it like store rest foot. Okay, we're going to store it, and we're going to say store rest object, actually, so that we can do this later. So by default, it's taking the geometry and plugging it into the geometry, but we want to take a different geometry and plug it into the geometry. Just like this is our reference object. This is our rest object. I'm going to put this in here. So what we want to do is grab, say, the foot anim, make it relative. Now this is grabbing the topology at every single frame. You can see here where you can see the position updating every frame. We don't want that at the vertex level. We don't want that. We want to store it on the very first frame. And again, this is like our time shift instead of Houdini. So we're going to say bake. And by default, this is bake still. And we're going to make sure this is frame 1. And we're going to bake it. Okay, it's baked that one frame, and this guy is our new rest data. So this is our new rest foot 2, and that's basically it. But what we can do is we can actually put this object into here so that we can store any object into here. So we can say, hey, actually I want rest foot this one instead, and then I want to bake that one on frame 1, say. And now this is our new rest foot here. So you can do that. And that's how I made this rest foot here. Okay, so by default, you're gonna see something like this in the geometry nodes whenever you set it. So it's assuming that this name, this is really just a string, and it's going into the named attribute, which is just rest position. It's assuming that it already exists on the geometry that it's coming from. It's assuming that it's really coming from the deforming geometry, but we're gonna assume that it doesn't exist. So for that, we're going to grab our rest foot 2, make it relative so that if there's any like local transforms, it'll inherit that. And we will say sample index. This is the geometry we want it from. We want to grab a vector. We want to grab the position vector. So this is super similar to the attribute copy. Essentially, what we're doing inside of here is essentially like we're grabbing P, or rather rest position, and we're doing it by the index or ID inside of Houdini. This is basically the exact same thing we're trying to do inside of Blender. So we're going to grab the sample index. The index is not going to be 0. It's going to be the actual index of, because these two topologies line up perfectly. So this rest 2 is the same exact topology as the foot anim. The point count doesn't change, the primitive number doesn't change, everything stays exactly the same. So that's why we're able to do this. So we're gonna grab the index, we're gonna grab the rest foot 2, and then we can actually do a group input here, group input, and we can call this rest foot. So I'm gonna go over here, we can call this rest object. I already have one here, so I don't need to do that, but you could if you, that's how I did it. And that way it's put up here. And then we'll just simply grab this. This is the rest position, because again, we're grabbing it from the rest foot. And we'll just say here, we'll say store named, not grid, store named attribute. We're gonna place it here. And then we're just gonna change this to a vector. We're gonna put this here. And then this name, we can actually just put into here. It's just rest position. You can also just type it out if you want. And now it works. Actually, this is incorrect. We need to do group input and not rest foot 2. We need to make sure it's the actual correct rest foot. My fault. So just make sure rest object is rest foot, which is what it's originally supposed to be from. So that's my fault. Because here I put in the wrong rest foot, which was shot 20, which was in a different space. So we need to make sure it's the rest foot. This is getting a little convoluted because of all the changes that I made here. So let's actually delete this and delete these two just for ease of use. So we're grabbing the rest foot, which is again foot anim, just frozen on one frame, foot anim. We're grabbing convex foot. We want to point deform the rest object, which is rest foot, over to here, and we are storing the name attribute, and there we go. So it should be working. And we need to put the surface object into it, so foot anim. And now it should not give us an error. Yes. Okay, great. This is all you need to do to set it up, okay? And again, this is just like the attribute copy inside of Houdini. So for those interested, I wanted to break down a little bit about how it works. So essentially, he's creating a stable transform using vectors calculated from the topology of the object. One vector is the normal of the primitive, which is, let me go back to annotate mode. Normal of the primitive is the vector that's pointing away from the primitive, and it's perpendicular to it. There's another vector, which is the tangent to the face, which is a vector pointing perpendicular to that normal, and it's moving sideways on the primitive. And then there's also the bitangent, which is perpendicular to both of these normals, or vectors, sorry, and this is pointing up the face. And it could depend based on the winding order of where these vectors are pointing, and also the neighboring point, like the neighboring faces, how they are constructed. So it might be that the tangent for this face might be pointing up and the bitangent might be going this way. It doesn't really matter as long as the vectors are all stable. So this is what we need to create a stable transform or a stable rotation. We need 3 stable vectors that are used on the topology of the object to create that stable rotation. The last vector is the position vector, which is what we're all used to seeing, which is what we actually see in the viewport when something's moving. This is just the position. So the position vector is, it's just the world space position in space. So here, instead of Houdini, I wanted to show you a simple visualizer for how this works. So we have our normal, our bitangent, and our tangent. So the tangent is red, bitangent is light blue, and normal is green. And so we can actually see how these vectors are constructed. And there's a polyframe node, which really just takes care of all this stuff for you. So you can see, based on these different styles, we can construct different vectors based on the primitive. Centroid, the first edge. The first edge makes most sense. As you can see, it's along the edge of the actual primitive. So let's keep it to that to keep it simple. So if we maximize this, zoom out a bit to look at it, we can see we have our normal, bitangent, and tangent all in these different colors. So you can see that the normal is pointing away. The tangent is in red. So the tangent on some of these, the tangent is going sideways, and others it's going down the face. It depends again on neighboring faces, how it's constructed, but the normal typically always points away from the primitive. And we can see this is the stable rotation vector transform that we've created. And then when I move in my timeline, you can see they all move with the foot. So you can see how stable it is. It's super stable. It doesn't flip or anything. And that's because it's based on the topology of the actual object itself. So what we're doing when we're doing this point deform is, if we have a point that is, let's say we have a point that's up here, we create this point and we move it up here. And if we were to try to say, hey, move this point here relative to how this foot is moving, what we would need is we would need to say, hey, okay, well, grab the closest point on this foot. Let's see, the foot is here. Let's move it a little bit closer. Let's say we grab it here. So let's actually construct it. You know what? Let's actually construct it. So what I'm going to do is I'm going to use the same method that he's doing so I can show you. So if I say float xyzdist, this is the same method that he's doing. It's just a different function name inside of Houdini. So if I go in here and I look at what he's doing here, this points to form, he's using a sample nearest surface, which if you're coming from Houdini, this is the same thing as what I'm about to do here. So it's XYZ. So we'll call this dist. I actually have a function for this. So let's just write that function. And just to make this a little bit faster, we have our prim, we have our UV. This is going to grab the closest P and N. So let's actually do the tangent and bitangent as well, so we can look at that. And now if I just create those actual attributes, we can do that here. Bitangent is bitangent. And now we'll actually be able to see, so this orient is turned on, so I'm going to cut that off. And we're going to look at these tangents. There we go. And now we can see, if I template this and I view this, we can see that when I move my point, we can see that essentially what this is doing is it's grabbing the closest primitive and the closest position on that primitive, and it's interpolating all three of those attributes according to the nearest surface. You can see what's happening. So essentially what this is doing inside of Blender, so I actually built a simpler example here. So here I have a single point and I'm sampling the same vectors on this sphere. So essentially looking at one single primitive here, you can see that there's 4 different vectors on this one primitive. There's this vector, this normal, and this normal. Now, depending on where I am on this primitive surface, it'll give me a different vector. So if I'm closer to this particular point, it'll give me a vector, a normal that's closer to this point normal. If I'm closer in the middle, it'll give me a more weighted average of all 4 point normals. If I'm closer to this point, it'll give me a weighted normal closer to this point, and so on. And so you can see what's kind of happening as I move my mouse, depending on the closeness that this point is to each point on the primitive, it'll weight all those vectors differently according to the weight at which, how close it is to each point. So at this point, it is the weight of this particular point is 1, so it's going to receive 100% of all of its vectors. And at this point, it's 100% of all those vectors, etc. So it just weights it depending on how close it is to those primitives. And that's basically all it does. So that is the sample nearest surface function. Now, to add on to this, once you construct the vectors on the rest geometry and you construct the same vectors on the deforming geometry, you are now able to construct a difference transform, which is what is the difference between these two stable rotations. You also have the position vectors, which is the fourth vector we are concerned with. So you have a rotation transform and a translate transform, and we want to combine these two together for both the rest geometry and the deforming geometry to get a complete picture of how the object is moving in space. So that's what this combined transform is doing. It's taking the deformed normal and the deformed tangent. So when the object is moving, what are its normal and tangent? Create a rotation, or rather construct a rotation or orientation based on those two vectors and create a matrix. A matrix is that complete picture I was talking about that combines both the rotation and position into a single object. A matrix doesn't have to be both rotation and position, but in this case it's very useful because that is what we want. We want a complete picture, and this matrix makes it much easier to manipulate data because you can simply multiply it by a vector and it would completely change the output. So in Houdini, to show a lot more clearly what's going on, I essentially tried to recreate his surface deformer into this one single wrangle with one code to try to much more clearly show what's going on. So first, we sample using this sample nearest surface. In Houdini, it is 2 functions instead of 1, which is actually very useful because it allows us to do more things. But we sample the nearest surface, all the vectors needed to create that complete picture. So we sample the normal, we sample the tangent, and we sample the position. Now in Houdini, it's a little different because we don't have to sample only from the rest geometry. In Blender, he's forced to sample from the rest geometry, but in Houdini, yes, we are sampling from the rest geometry, but we can store, in Houdini, we can store where a point is located closest to and on a primitive, store that location, and find data on another piece of geometry that has the same topology. So let me show you what I mean. If I move this point, so here I've made one modification in my code to force the position to snap to the closest surface found of this other primitive that we found. So to show you, if I move this point here and I try to move it out, ignore these lines here. I know it's confusing just because it's showing this operator here. But if we look at just this point, you can see no matter how I constrain my point to move away from the primitive, it's forcing it to snap directly to it. And this again is just to show you like what's happening. So it's essentially, it's sampling, okay, this point is, okay, this is the location found on that primitive. So this is the location found on that primitive. Once you have that location, store that location reference, where that location was on that primitive so that we can use it elsewhere. That's what this prim and this prim UV output. The prim is a primitive number, so it is the primitive ID. So every single one of these primitives is unique. Not every one of these has the same primitive ID. We can actually look at them inside of Houdini. This primitive ID is 83, I believe. It's hard to read. Maybe 93. It's hard to read it. And the UV is that weight that I was talking about earlier, which is a 2D vector going from 0 to 1. It is essentially a normalized UV for each primitive. Once we have that primitive location information, we can use that information for another set of geometry that matches topology. Here I set up another branch where I have the same sphere but with a transform after it. Here I've changed the code a bit to sample the position from the second input sphere instead of the first. You can see the 2 there instead of the 1. So this is 1 and this is 2, the different inputs. I can move this other sphere, and while I do that, the point will use that previously found primitive location data to sample, to do like a reverse lookup and say, hey, I know you sampled from the rest geometry, But using the location data on this other geometry, what is the position? So that's essentially what we're allowed to do here. And so it's taking that, it's taking that, the same location data, and it remembers it. And it's like, hey, what is the location on this other geometry? And so that's what this is doing. Now in Blender, this functionality is not quite there. The xyzdist and the primitive UV functions are wrapped into one, into that sample nearest surface. They're wrapped into one, which means this particular functionality where you can sample from one geometry and store that location data and then use that location data in another piece of geometry that matches topology, you can't do that in Blender. So instead, what you're forced to do is you're forced to store all the attributes on one set of geometry. It would need to be on the rest geometry that the points are closest to. So you would need to take all this information on this branch and put it into this branch and just make sure to sample all that information here. So that's what you're forced to do in Blender. So to finish how this works in Houdini, this makeshift point deform that I built, we sample all the attributes required to create the rotation and position data for both sets. The rest geometry, input 1, and the deforming geometry, input 2. Rest and deforming. So after we sample all the needed attributes for both the rotation and the position here, we use another function called makeTransform, which is a super useful function, and it's very similar to the combine transform function in Blender. So this is the combine transform. It's basically, there's an option. There's several ways you can construct this function, or different arguments you can use, but one of the options is to use 3 vectors, which is 2 rotation vectors and then a position vectors, and you can construct a 4x4 matrix out of that. So here we have our normal 1, our tangent 1, and our position 1. So the normal one is what is the rest normal, so the non-moving normal, like it doesn't move at all, it never moves in space. And what is the rest tangent, so again that face tangent we talked about earlier. And then what is the rest position. And then we construct a deforming matrix, which is what is the deforming normal, or what is the normal that's moving in space over time, what is the deforming tangent, that face tangent, and then what is the deforming position, or what is this position in space. And you now have these 2 4x4 matrices, which you can actually subtract. So how you subtract matrices in Blender and Houdini is you invert the rest one and then you multiply the other one. So it's just like if you have vector 1 and you want to subtract like the to and from, so you say to subtract by the from, and that gives you the vector, that gives you the difference between the 2 vectors, right? Well, when you invert a matrix and multiply it by another matrix, that gives you the difference between those 2 matrices. So what is the difference between the rest geometry and the deforming geometry? And what is that difference? And we're saying M here. So M is that difference matrix or transform. So when we multiply the position vector by M, multiplies equals means it's essentially a short for saying equals P times this. It's P equals P times M. Again, this is what we need. This is the invert M1 times what? Invert the rest matrix and multiply it by the deforming matrix. That says, hey, what is the difference between these 2 matrices? And that's it. That's all we need to create a makeshift point deform inside of Houdini. This is essentially what you need. So yeah, just wanted to go in a little bit more detail, a deep dive, if you will, if you wanted to know more about how this kind of stuff works. I really hope this was helpful to somebody out there. Like and subscribe to my channel if you found it useful. I am going to start trying to put out more tutorials soon. But yeah, so just subscribe to my channel so you can stay informed. I plan on putting more Blender tutorials out there, at least showing my point infection tool. And yeah, I hope this guide helps someone. Thanks for watching and have a good one.